Greetings, Planeteers. What is up, everybody? This is Tumelo Ramolula, and I'll be giving you guys the critical eye from the science guy. This is a special code talk that is going to be provided, focusing on the circulating atmosphere. So let's go right into it. Right. So the core talk that was presented by Dr. Kabir last week spoke about the circulating atmosphere. In this talk, we learned that the motion of the atmosphere is what enables distribution of heat that is trapped by the greenhouse effect to be distributed across the entire planet. So we learned that the distribution of warm and cold air, it aids in the offsetting of the temperature differences that Dr. Kabir spoke about across the planet, right? We also learned that this three-cell circulation model gives a clearer understanding of the way the atmosphere actually circulates. And then lastly, we also spoke about the fact that the circulating atmosphere determines the weather, climate conditions, as well as the biomes that we experience. So in this talk, I'm going to be giving a closer look at how exactly do we actually break down the single cell into three cells. And I'm also going to look at the importance of the intertropical convergence zone, as well as how exactly does the atmospheric circulation impact and determine rather the weather and the climate conditions that we experience. So that's what we're going to be looking at in this talk. And then lastly, we're going to also look at the special South Africa. What is it about South Africa that makes it special with regard to the circulating atmosphere? All right. So Dr. Kabir explained to us that we have the three-cell circulation model, and this is what explains how our planet is actually experiencing atmospheric circulation. So we looked at the fact that we have a low pressure belt at the 0 degree equator line. And this is because we experience low pressure because the air is actually rising due to the fact that the equator in this model is directly receiving sunlight from the sun. So this heat that heats up the air particles in the lower part of the atmosphere gives them energy, and therefore they rise, and then they end up sinking when they go towards the 30-degree lines north and south of the equator. And because this air is going to circulate back towards the equator, we have what we call the Hadley cell. And this is what Dr. Kabir explained last week. And he also explained how we see the same thing happening between the 30-degree line and the 60-degree line, as well as the 60-degree line and the 90-degree line. That is how we have our polar and our ferro cells, right? So I started to ask myself a question as a critical guy, and I wanted to find out when we started understanding circulating atmosphere, we actually saw a gigantic single cell model that was applied on one half of our hemisphere, right, on the northern and the southern part of the hemisphere. So how did we go from one single cell to three cells? I understand the fact that we have cold air at the poles and we have warm air at the equator. And so this temperature gradient is going to cause the air to move from hot to cold. So that means that the air is going to move from the equator to the poles. So what I didn't understand was why that air stopped at 30 degrees and also at 60 degrees. Why did we break down the single cell into three cells? And then I started to think about it. What we saw from the three-cell circulation model is that at 0 degrees we have low pressure, at 30 degrees we have high pressure, and at 60 degrees we also have low pressure, and at 90 degrees we have high pressure again. So what I started to realize that there must exist a pressure gradient, and that must contribute to the way in which we break down the single cell into the three-cell circulation model. So the air that is moving from the equator, as it rises, it loses its energy, right? And so it moves further and further away from the equator into the upper atmosphere, where it then ends up not having energy and it decides to diverge, right? Because when it was rising as one large air mass, but when it gets to the upper atmosphere, the air mass then diverges, right? And it goes to the 30-degree lines north and south of the equator. I thought about it and said to myself, the air is losing its energy, and that is why it is not going to reach the 90-degree line or the pole, right? So because of that, it starts to get tired, and therefore it then sinks at the 30-degree line. That is what probably causes the reason why we see the high pressure cells at the 30-degree line and the low pressure cells at the 60-degree line. The air does not have enough energy to travel all the way from the equator to the poles. So this is why we have the bands of high pressure cells that form along the 30-degree lines north and south of our equator, because the air gets tired and it sinks, right? The sinking polar air at the 90-degree line is also going to rise when it reaches the 60-degree line, because the air that was sinking from the 30-degree line and diverging when it meets the Earth's surface has to go somewhere. It is not going to diverge forever. And so it bumps and clashes with the air that is coming, that is sinking from the 90-degree line. And that is why we see air rising at the 60-degree line. So this is not necessarily due to the fact that there's more warmth at the 60-degree line as compared to the 0-degree line, but rather the rising air is rising because of the fact that it crashes with the air from the 90-degree line as well as the air from the 30-degree line that were diverging. This is why we then have a low pressure band that is forming at the 60-degree line, north and south of our equator. All right. So this is how the air is going to actually move, and this explains better why we actually have a three-cell circulation and not just one gigantic cell on one half of our Earth's surface or the hemispheres, right? So the pressure gradient can also be seen when you look at the planetary motion of the air, not just as it rises from the bottom of the atmosphere to the upper atmosphere, but also when as it moves from one latitude line to another, right? So we're going to then apply the concept of the pressure gradient here. So at 30 degrees, we know that we experience sinking air, right? And so that means that there's a high pressure there. And at 0 degrees, we have low pressure because the air is rising. So as we understand the temperature gradient, where heat is going to move from a place that has high energy to low energy, pressure acts the same way, right? So it's going to move from the high pressure cell towards the low pressure. Air moves from where there's high pressure to low pressure. So that's what the pressure gradient, that's the concept of the pressure gradient. And this pressure gradient that exists, it also further induces the prevailing surface winds that we experience. So in as much as air is rising from the Earth's surface to the upper atmosphere and it sinks towards the 30-degree lines, right? So that means that sort of illustrates that the air is moving from the equator to the 30-degree line. That is actually what's happening in the upper atmosphere. In the lower atmosphere, the pressure gradient is what is going to force the prevailing surface winds that we actually experience. And that is why we see air moving from the high pressure cells to the low pressure cells, right? And so that is why we see air moving from the 30-degree line to the equator. And the same is applied between the 30-degree line and the 60-degree line, where air is moving from high pressure to low pressure, and so it's moving that way. The prevailing surface winds are moving that way, right? So that provided me with a better understanding of why the single cell circulation model was actually broken down. This is because of the pressure gradient that we see being applied. And lastly, from the 90-degree to the 60-degree, we see the exact same thing happening where air is actually moving. The surface winds are moving from the 90 degrees, they're moving toward the 60-degree line. So when we look at now a better way of even understanding and naming these winds, we see that there is between the 0-degree and the 30-degree line, we see the northeast trade winds, right? So they're moving from the northeast towards the southwest. That is how winds are named when we're naming them. They're named from where they come from. And in the southern hemisphere, between the 0-degree line and the 30-degree line, we see that the air is moving from the south towards the north. So that means that the air is moving southeasterly, and that is why they are known as southeasterly trade winds, right? And the westerlies are the same that are being seen when they're flowing from the west towards the east. This is between 30 degrees and 60 degrees south of the equator. And then you also see the polar easterlies that are being named because they're coming from the pole, and from the eastern side, they're flowing towards the west. And that is where we also see the effect of the Coriolis force. The air is not just moving in a straight motion from high pressure to low pressure, but it actually curves, right, towards wherever it is going. So that's when Dr. Kabir was talking about the Coriolis force and how it also impacts the way in which our winds move. There's something else here that we actually notice with the surface winds that are prevailing. As the air is moving from the 30 degrees line to the equator, north and south of the equator, these air masses actually clash, right, at the equator, and so they rise. The same thing that we were seeing happening at the polars. So as the air is clashing and rising at the equator, we call that the intertropical convergence zone. This is because the equator is between the two tropics, and this is right where the air masses actually converge. So it is known as the intertropical convergence zone. This concept is very important to understand because this is where we begin to understand how our seasons actually occur between the northern hemisphere and the southern hemisphere. So the intertropical convergence zone is where air masses are converging from the 30-degree line, so north and south of the equator, at the equator, causing unstable weather conditions. So this is exactly what explains what I just explained right now. The surface winds that move towards the equator, they result in the convergence of the air, and therefore it rises. This rising air is also exacerbated by the heat at the equator. So the reason why we have a difference between what happens at the 60-degree line and the equator is because at the equator, the we have a lot more energy that is being absorbed by the earth because the sun is closest there, right? And so we have a lot of heat. That is the concept of the temperature gradient. And so the heat at the equator is the reason why the air is also going to rise even more. That is why we actually experience more unstable weather conditions across the equator as compared to at the 60-degree line, where we also see rising air, right? But that's still is explained here. These clouds here that they're illustrating that at the equator where we're having rising air, that's where we experience unstable weather conditions, and these are thunderstorms, rainfall, and because this is because of the cooling air that was rising, right? So as it cools, it begins to form clouds that cause the unstable weather conditions that are experienced at the equator, also at the intertropical convergence zone. So now when we look at our two diagrams over here, the one on the left is showing us what our model is now depicting as we begin to understand the intertropical convergence zone at the equatorial band, at the equator, and we call it here the equatorial low because we have a band of low pressure cells running across the equator. At the 30-degree line, we have the subtropical high because it is just outside the tropics, and we have a band of high pressure there. And then at the 60-degree line, we also have the subpolar low because we have a band of low pressure cells just outside of the polar region. And right at the poles, we have a polar high, right? So that is where we have a high pressure cell right at the poles due to the cold air that is sinking. So this is what our model shows. But when we actually apply a bit of topography, we begin to understand that we will actually experience a bit more of a change in the way the winds move. So they don't strictly move exactly as depicted in the model. They have a bit of a better way of moving due to the fact that there are other impacts that are applied to the air masses, such as topography. So we will take a recap now and try to remember what we actually associate with our low pressure and our high pressure cells in the bands that I've been talking about. So like I've been saying, a low pressure cell is associated with moist warm air that is rising and it cools, forming unstable conditions. So wherever there's low pressure, we're going to expect unstable conditions. Where there's high pressure, we experience sinking air. And so because the air is sinking, it is drier and it is much more colder. So the conditions that are experienced there are not as unstable as the conditions that we experience in a low pressure cell. So in a high pressure cell, the conditions are calmer, a bit warmer, yes, because as the air is sinking, it begins to warm up, but it's much more drier. There's not much rain or unstable instability in the weather conditions. So it's important to understand these concepts as we begin to look at how the intertropical convergence zone works, right? And how it contributes to the season, right? So We know that we have seasons. We do not experience weather in a consistent way where at the equator it is always hot and at the poles it is always cold. And in between, the subtropics and the subpolars are not always experiencing high pressure conditions or low pressure conditions. This is because of two reasons. One is the fact that our Earth is actually at a tilt and not standing up straight. So if you look at our model again, the model depicts our Earth to be standing straight on its axis. But in reality, we know that our Earth is actually at an axis. And this axis is the reason why we experience different weather conditions. Because when our Earth being at an axis means that the sun does not hit every single region in the same way anymore. All right? And the other reason is the fact that our Earth actually rotates around the sun. And so in its rotation around the sun, we see that different parts of our Earth's surface are heated in different times. So at the same time, the different parts of the Earth do not receive the same amount of heat because it is in its rotational mode, right? So those are the two reasons that we're going to be exploring right now and why they actually produce the different seasons. So the circulation of the Earth at its axis, right, means that when we look at our dates and how we actually experience our seasons, we'll know that our spring and our summer actually begin between September and they end in February, right? That is for the southern hemisphere. And our winter begins in in March because of the kickoff of the autumn, and it ends in August, right? So that is the period in which we actually receive our winter. So let us start with the winter and look at what happens in the southern hemisphere during the winter season, during the period between March and August, right? So during this time, the Earth is spinning in its axis and it's also rotating around the sun, right? So we still do get our daily diurnal changes between day and night, but we are actually not receiving as much sunlight as we do in summertime because during that time the Earth is shining, the sun is shining more towards the northern hemisphere, right? Because the northern hemisphere is tilting towards the sun. The tilt of the northern hemisphere towards the sun means that we are tilting away from the sun. And so even though we do get the light, we don't get as much heat, right? So more of the heat is being distributed to the northern hemisphere. And so because we have cooler temperatures during that time, that is when we also experience our winter solstice, June 21st, right? So on the 21st of June, that is when we experience our winter solstice because that is when we are most furthest away from the sun. During this time, the sun is directly overhead the 30-degree north latitude line, and that is where the intertropical zone is actually located. So remember that the intertropical zone is also exacerbated by the fact that the sun is hitting the equator, right, when our model was straight. But now because we have a tilted Earth, it is actually hitting at the 30-degree latitude line north of the equator. And so our intertropical zone moves towards that area during that time. And so that is why we experience the weather conditions that we experience, such as Cape Town receiving rain, whereas the rest of the country is actually dry. So the Cape Town receiving rain during that time is because as the intertropical convergence zone moves up, so do all the other wind belts that we see. So the 60-degree low pressure cells move further up and they don't just stay stagnant. The 30-degree south of the equator latitude line also moves further up. So the mid-latitude cyclones that we experience that are associated with the low pressure cells at the 60-degree line begin to actually have an impact at the coast of South Africa, right? So this is where Cape Town is, and that is where Cape Town begins to receive rain. So unstable conditions are associated with the low pressure cells, like we said, but now because they are moving further from the 60-degree line towards the 30-degree line due to the move of the intertropical zone from the equator towards the 30-degree line north of the equator, we see the impact of the low pressure cells that are supposedly should be seen on the 60-degree line. And so that's why we have unstable weather conditions in winter at Cape Town. You see, when we flip the script around and we actually have the southern hemisphere facing the sun, we begin to experience warmer conditions around the southern hemisphere, and that is when the spring and summer seasons begin. That is between the months of September and February. So during this time, that's when we also experience our summer solstice, which is on the 21st of December. During this time, the sun is overhead at 30 degrees south, right? So due to the fact that our planet is tilted, we see that the intertropical zone then moves further down away from the equator towards the 30-degree line south of the equator. This is where we then begin to see exacerbated rainfall in the northern parts of South Africa rather, and we see rainfall that is falling across the province of Limpopo. So the entire country actually gets to experience this weather, that we have exacerbated rainfall in Limpopo during this time. This is because the intertropical convergence zone is actually directly at the 30-degree line south of the equator. So this tilting of the earth towards the sun during this time, that is making it that enables the southern hemisphere to experience warmer conditions. It means that in the northern hemisphere, the conditions are much different. Right? This is because this part of the earth is facing the sun, and yet the northern hemisphere is facing away from the sun, which means that the northern hemisphere is now beginning to experience cooler conditions during this time. That is why near Christmas has snow, while we have great summer weather during our Christmas period. So when we actually look at this entire example that we've just used to explain what happens during the summer and winter solstice periods and where the position of the intertropical convergence zone is, we see that our country actually experiences particularly different weather conditions. So when we think back to what we explained or what we began to understand about what happens during the winter season at Cape Town, we experience rain, right? And so this is weird because the rest of the country during the winter period does not actually experience rain, but the Cape Town region experiences rain because of its particular position along the 30-degree line, and the fact that the intertropical convergence zone moving further north means that the low pressure cells that are experienced in the 60-degree line actually begin to be experienced right by the coastal region of South Africa. So this makes South Africa special in that we are able to experience, even in the same season, differences in weather conditions that we see due to the fact that we're positioned directly where the intertropical convergence zones movement can actually affect us. And so that's what we see during the dry season, right? And during the wet season, we get to experience really great rainfall that we receive during the rainfall period, because ITCZ dips further lower than just at the equator. It dips towards the Tropic of Capricorn, and we receive great rainfall in the northern regions of our country. So that's what makes South Africa special with regards to the way in which the intertropical convergence zone behaves in the winter and the summer seasons. Excuse me. So this diagram actually shows us this phenomenon in a much better way, where we actually see the high pressure cells and the low pressure cells as they move further up or further down during the winter and the summer regions, during the winter and the summer season. So as we can see here, this is our country, South Africa, and below it we have a low pressure cell that is actually supposed to be further down, but because this is during the winter period, we see that our low pressure cell is moving up as the intertropical convergence zone has also moved up. So that's where we begin to actually experience the weather that we experience, such as the rains that we've spoken about in Cape Town, as well as cold fronts that actually hit us in the rest of the country. These cold fronts come with the low pressure cells that have migrated from the 60-degree line. What we also know, however, is that we should be experiencing the high pressure cells, right? Because we're close to the 30-degree line. So this is what causes the lack of rainfall during the winter periods in the interior of the country, because it's just sinking due to the high pressure cells that we know and we normally experience, right? And in the in the in the summer time, we know that these pressure systems move further down because the intertropical convergence zone has also migrated towards the 30-degree south of the equator line. And so that is why we then no longer experience any cold fronts, because this tropical cyclone, latitude cyclone that we see here, not tropical cyclone, this latitude cyclone that we see here moves further down. And so during the summertime, we don't experience any um, cold cold fronts that come with the latitude cyclone. Instead, we actually get to experience rainfall from the easterly wave low that moves also further down during the summertime. And then that's why we also don't have much colder weather or that is dry, because the high pressure cells that are known as the subtropical South Atlantic high and the South Indian high move further low. So we don't actually experience any dry conditions, but rather we experience rain. And so this is what makes South Africa even more special, right, as we've already discussed. So in closing, let's look at what we've learned so far by taking a critical look at the circulating atmosphere taught by Dr. Kabir. We learned that not just the temperature gradient is going to influence our atmospheric circulation, but the planetary winds that we experience, the surface winds that prevail, are actually forced even more by the pressure gradient, right? Because we have the bands of high pressure and low pressure across our planet, and so the air forces itself to move from high pressure to low pressure due to the gradient that is existing, and that is why we see the different planetary winds that we experience. We also learned about the intertropical convergence zone, wherein the convergence of air at the equator from the 30-degree north and south of the equator, um, this convergence is going to cause a rising of air, right? And so we learned that the intertropical convergence zone does not actually remain at the equator, but rather it shifts due to the fact that our Earth is at a tilt. We also learned that the tilt of the Earth is one of the other reasons why we experience seasons. Wherein the first reason is that we experience our Earth to be rotating around the sun. So the tilt of the Earth and its rotation around the sun cause the way in which we experience our seasons in the northern hemisphere and the southern hemisphere. What we learned to be special about South Africa is that it is located at a particular point by the 30-degree latitude line, which enables it to experience different weather conditions because of the way in which the intertropical convergence zone moves. So I hope that with this talk, we are now able to understand better why we have seasons during that are influenced by the circulating atmosphere, and also the other forces that contribute to the circulating atmosphere, not just the temperature gradient. This has been a great talk, and I hope you got to learn something, guys.